Hello everybody, welcome into another lesson. So today we are going to talk about polygons. Well, what are polygons? It's nothing more than a figure that consists of end-to-end line segments. They connect end-to-end to create a closed figure. And they are straight lines on each side. So a triangle, for example, that's a polygon because it has line segments that connect end to end, side to side. That is the least number of sides a polygon could have, by the way, is 3. Then here we have a pentagon with 5 sides. It's still a closed figure with line segments connecting end to end. Then of course we have a parallelogram that's got 4 sides. It's a polygon. But let's talk about what a polygon is not. We got 2 examples of open figures here. We have your classic angle, and then this looks like an open square. If it's open, it's not a polygon, because a polygon is a closed figure. This one here, it looks like a polygon, but it's got a round top. It's got a curved top. A polygon has no curves in it. There's no curvature. It's just straight line segments connected end to end to form sides. And this figure down here is also not a polygon because you have sides overlapping. The sides of in order to have a polygon, the sides can't overlap. You have this side crossing with this side, which makes it not a polygon. So a polygon, again, it's a group of line segments that are connected end to end, not in the middle, but end to end, that form a closed figure. So we have covered lots and lots of triangles, and yesterday we covered quadrilaterals. Today, let's talk about polygons in general. Let's start with some figures that have greater than 4 sides, such as a pentagon. I put the prefixes here. Penta means 5, hexa means 6, hepta means 7, octa means 8, nona means 9, deca means 10. So a pentagon. We have a pentagon here. Alright, this here, being a 5-sided figure, is called a pentagon. This is a pentagon. It's got 5 sides. And to be more specific, this is a regular pentagon. What does it mean to be a regular pentagon? It means all the angles are congruent to each other. So it's equiangular and all the sides are congruent to each other. If you have a regular polygon in general, this goes for whether it's a hexagon, a heptagon, a triangle, a quadrilateral. If it is a regular polygon, I'm going to write this here. Regular polygon. It is going to be equilateral. Equilateral means all the sides are congruent. It is also going to be equiangular. It'll be equiangular, meaning all the interior angles of the polygon will be congruent to each other. That's how you have a regular polygon. In this case, we have a regular pentagon. And we will talk more about angles of polygons here in a minute. Now I'm going to try to draw a hexagon. Alright. Let's go ahead and try to do that. Well, I did the best I could there. It's a six-sided figure. It's a hexagon. This will be a hexagon. It is a six-sided figure. So that's what a regular hexagon looks like. It'd be equiangular and equal-sided. Let's see, how do I draw a heptagon? I'm going to look these up, that way I could draw them accurately. I know how many sides each of them have, I just want to see a good visual representation. Sure looks like a mess. Alright, so according to what I'm pulling up here, it is something... It is something like this. So there is a heptagon. It's got 7 sides. A heptagon. In this case, it's not a regular heptagon because you can clearly tell the sides aren't congruent. This is a regular heptagon. This is not a regular heptagon, rather. This is just a heptagon, but it's not a regular heptagon because the sides are not congruent to each other. Therefore, it's also not equiangular. Heptagons, once you get past hexagons, it gets pretty hard to start drawing some of these. Let me look up an octagon. I want to draw all the way to a decagon. We're gonna stop after decagons. Alright, I think I got it. Not quite that steep. I'm not able to draw them. But as you see, once you get beyond 6 sides, it really starts to become a mess. So, basically, 8-sided figure would be an octagon. A 9-sided figure would be... So, octagon would have 8 sides. A nonagon would have 9 sides. And then, of course, a decagon would have 10 sides. Okay? Once you get beyond 10 sides, there are technical scientific names for each of the sides after that, but they're loan-worded, they're from Latin. You really probably don't want to have to use them. So, once you get past 10, you would just call it an 11gon. 11gon, it's got 11 sides. Then you have a 50gon. You could have a 50gon, and don't even try to draw those. That would be horrific. It has 50 sides. Yes, I suppose you could even have a 100gon. It would have 50 sides. I mean, 50 sides, 100 sides. What am I saying? A 100gon would have 100 sides. Boy, oh boy. Alright. So yes, once you get past 10 sides, you just call it an 11gon, or a 12gon, or a 50gon, or a 100gon. That's what you would call any figure that has greater than 10 sides, just by the number of sides then gon. So, that would be... So that's basically I've shown you what some of the polygons look like. I've explained about the sides and what you call them. I have the prefix list up here. Now, let's get into angles. So, sum of interior angles, that means angles of a polygon. Alright, so if you want to find the sum of the interior angles of a polygon, there is a formula for that. I'm going to write it in different color. Let's see, let n equal number of sides polygon has. So what you're going to do is you're going to take the number of sides a polygon has, subtract 2 from that, and you're going to multiply it by 180 degrees. So basically in this formula, n is the number of sides a polygon has. You take the number of sides, you subtract 2 from that number of sides, then you take that whole quantity and multiply it times 180 degrees. So, for example, let's say we want to find a triangle, right? Let's solve for, we know it's going to be 180, but why is it 180? So, the number of sides a triangle has is 3. You're going to subtract 2 from that, multiply it by 180 degrees. Well, 3 times 2, that's going to be 1 times 180 degrees, which would then, the sum of the interior angles of a triangle is, in fact, 180 degrees. So we've solved the triangle. If you stick 4 in there instead of 3, you would get 2 times 180. You get 360 degrees for a quadrilateral. Well, we'll do a quadrilateral. So then we have a quadrilateral. If we want to do a quadrilateral, you take the number of sides, which would be 4, subtract 2 from that, you multiply that quantity by 180 degrees. Well, 4 minus 2, that's 2. So you would take that 2, multiply that by 180 degrees. 2 times 180, that's 360 degrees. So this is as we covered yesterday, the sum of the interior angles of a quadrilateral is 360 degrees. That's where we get that from. Alright, so this begs the question, what about a pentagon? What's the sum of the interior angles of a pentagon? Let's do a pentagon. So a pentagon has 5 sides. You subtract 2 from that. You're going to multiply that quantity times 180 degrees, which would have to mean 5 minus 2, that's 3. You'll take 3 times 180 degrees, which should give you 540. So the sum of the interior angles of a pentagon is going to be 540 degrees. Let's do a hexagon for good measure. Whoops, did not mean to punch that. So we'll do a hexagon. A hexagon has 6 sides, so we'll take the number of sides being 6 minus 2. We're to multiply that quantity times 180 degrees. So 6 minus 2, well, that's going to be 4. We'll take 4, we'll multiply that times 180 degrees, which would be 720. So the sum of the interior angles of a regular, of a hexagon in general, would be 720 degrees. Alright, what if we did a 12-gon? A 12-gon means, of course, it's got 12 sides. So we'll take 12, this number of sides is 12, that minus 2, we'll take that quantity times 180 degrees. Well, in the parentheses, 12 minus 2, that's 10. You'll take that 10 times 180 degrees. 10 times 180, that's going to be 1800 degrees, or 1800. So the sum of the interior angles of a 12-gon is 1800 degrees. So let's do one more for good measure. What about a 100-gon? So we'll do a 100-gon. So again, take your number of sides being 100, that minus 2, take that quantity times 180 degrees. Well, 100 minus 2, last time I checked, that was 98. Times, you take that times 180 degrees. And I'm sure it's going to be a god-awful number. It'll probably be not a pretty number. Alright. 98 times 180, yep. 17,640. So the sum of the interior angles of a 100-gon is going to be 17,640 degrees. So again, it's just this idea, if you want to find the sum of the interior angles of a polygon, you just take the number of sides, subtract 2 from that, multiply that whole quantity times 180, you'll get your answer. Alright, now, whoops, I had n minus 2 times 180. I should probably keep that up there, because what we're going to do next is we're going to deal only with regular polygons. We're going to find the measure of each angle of a regular polygon. If you remember when we talked about regular polygons, that means they're equilateral, meaning that all the sides are congruent to each other. That also means they're also equiangular, meaning the angles are all equal to each other. So let's say, for example, let's see here. So we will find the measure of an angle of a regular polygon. By the way, in case you haven't figured this out yet, the number of sides a polygon has is also the number of angles it has. So in any polygon, no matter how many sides you have, that's the same number of angles you will have. So what you'll do to find the measure of a single angle of a regular polygon, you're going to take your n minus 2 times 180. You'll take all that, you'll divide that by n. You'll divide that by the number of sides. That's the formula to find it. So let's say, for example, let's deal with the triangle again, because why not, right? Let's deal with the triangle again. So let's find an angle, just a single angle of an equilateral triangle. Assuming it's equilateral, you'll take that 3 minus 2 times 180 degrees. You'll divide that by the number of sides, being 3. Well, up top in the numerator, 3 minus 2 is 1. But 1 times 180 is just 180 degrees. all over 3. 180 divided by 3, that's 60 degrees. So for a triangle, a single angle of a regular triangle or an equilateral triangle is 60 degrees. And you would have 3 60-degree angles, they'd add up to 180. So that's correct. Alright, we'll do a quadrilateral again. Let's deal with a quadrilateral. Alright, so quadrilateral has 4 sides. We'll take that 4 minus 2 times that 180 degrees all over 4, because it's the number of sides is 4, so you divide it by 4. So in the numerator, 4 minus 2, that's going to be 2 times 180 degrees all over 4. Well, 2 times 180, that's 360 degrees all over 4. 360 divided by 4, that's 90. So each angle of a regular quadrilateral, meaning it's equiangular and equilateral, is 90. The only quadrilateral we know that fits that bill will be a square. So, because a square, if we remember from yesterday's lesson, is both equiangular, having 4 90-degree angles, and it has 4 equal sides. So, that's what you get for a quadrilateral. Alright. You know what? Some of these I'm going to have to move over here. Let's do a pentagon. Let's do a pentagon here, okay? Let's figure out a single angle of a regular pentagon. So still, take your 5 minus 2 times that 180 degrees, but you're going to divide it by 5 because it's got 5 sides. So in the numerator, 5 minus 2, that's 3. You would take 3 times 180 degrees all over 5. 3 times 180, that's 540. So you take 540 degrees, divide that by 5. Let me see what the heck that is. I think I know what it is, but let's just be sure. Yep, 108. So each angle of a regular pentagon has an angle measure of 108 degrees. Now for the final one, let's just amuse ourselves. Let's do a 100-gon. Let's go ahead and do that 100-gon. What do you say? So we're going to do a 100-gon. So again, take your number of sides in the parentheses, will be 100 minus 2, multiply that times 180 degrees, divide the whole thing by your number of sides, which would be 100. Okay. So in the numerator, 100 minus 2, that's 98. That'd be 98 times that 180 degrees. All over 100, because the number of sides is 100. Alright, I forget what 98 times 180 is. Let's look that up. 17,640. So you would take 17,640 degrees over 100. Because since it's a 100-sided figure, it's also going to have 100 angles that are equal to each other. 17,640 divided by 100, that's going to be 176.4 degrees. So each angle of a regular 100-gon would equal 176.4 degrees. That's almost a straight line. Almost. Very interesting how that works. For each angle, they're almost straight lines, but not quite. So again, we talked about polygons today. Polygons got to be closed figures that are formed by line segments back to back, end to end, that lead from one to another that form a straight closed figure. If it has a curve on it, it's not a polygon. If it's an open figure, it's not a polygon. If you got sides overlapping like that bow tie thing I drew, that's not a polygon because the sides overlap. And then what we did, we kind of drew some polygons, like some pentagons. Penta means 5, hexa means 6, hepta means 7, octa means 8, nona means 9, deca means 10. If you go beyond 10 sides, you just start calling it an 11-gon, a 12-gon, a 100-gon, a 500-gon, what have you. And then to find the sum of the interior angles of a polygon, you just take the number of sides that you have minus 2. You take the whole quantity, multiply it by 180. You'll get the sum of your interior angles of a polygon. Then we talked about regular polygons, which, if they're regular, that means they are equilateral and equiangular. So if you want to find the measure of an angle of a regular polygon, you take the number of sides minus 2 times 180. So just like you would to find the sum of the interior angles of a polygon, but you're going to divide that by the number of sides a polygon has. And then you'll get the measure for just one angle of a regular polygon. And they'll all have that same measure, so it wouldn't matter. They'll all have that same, every angle of a regular polygon is congruent, so they'll all have that degree measure. But that's it for polygons. Next lesson we are going to do area problems. We're going to do the area of a parallelogram, a triangle, and a trapezoid. We've already covered, actually earlier in the course, rectangles and squares. I don't think we need to spend time on that. Those are pretty simple. But we're going to do parallelograms, trapezoids, and triangles. So I hope everybody has a good night. Take care.